And now Michal will tell us about matrix multiplication.
Hi, thanks for coming, thanks for inviting me. So I would like to tell you something about Boolean matrix multiplication and about proving some lower bounds for it. And actually what we will prove some lower bounds for some combinatorial type of algorithms. So I will try to explain you what I mean. And this is a joint work with my student Deborah Tidas and Mike Sachs from Rutgers. So let me just remind you what Boolean matrix multiplication is, because so we would be on the same page. So by Boolean, of course, I mean that the values are just 0, 1, and then still the question is actually over which field. So it's actually not over a field, it's actually over this Boolean semi-ring, so it's basically ands and ors. So it's so you get two matrices which are 0, 1 matrices, and each entry Cij is basically this. You get working on these on the row here and on the particular column here, and basically you are taking, instead of taking multiplication, you are taking and then you are taking or over all these. So this is what we mean by Boolean matrix multiplication, and we would like to understand it a little bit better. So let me just actually just a quick remark. It actually basically corresponds, or it's closely related to deciding connectivity in, say, tripartite graphs, or in general, like actually in directed graphs of arbitrary size. But if you look on these tripartite graphs, imagine that the edge is actually just going from left to right, and you have three parts, A, B, C, there of, say, the same size, and you are just trying to figure out which vertices on the left are connected to which vertices on the right. So if you actually describe basically the connections over here by incidence matrix and connections over here also by incidence matrix, then the product of the two matrices PQ is exactly, gives you the connections from left to right, and that's exactly the Boolean matrix multiplication product. So that's actually what is it about. And people are interested in this because it actually captures a very natural problem people care about, and that's actually connectivity in directed graphs. So what can we say about algorithms for this problem? So of course a naive algorithm takes n cubed time, but there is much faster way, and that's actually starting with Strassen's algorithm all the way actually to like recent work of Legal. We do have an algorithm which actually works for this very fast, because you can actually just use the usual integer multiplication or multiplication of matrices over reals, and that basically is also going to give you as a byproduct actually this Boolean matrix multiplication.
It's
so if you,
totally obvious, right?
You have to think about it. Well,
the oldest I know is Adi Shamir that reduces the Boolean to the arithmetic, and it's in fact the first problem I know of approximating or by low degree polynomial. It just says Boolean.
Can you just multiply the two
over reals? I think it's trivial.
But this would be costly because the bits, the numbers will be big. At least I don't
modulo. You mean depends what kind of operations you get? Okay.
Yeah. When you want Boolean operation, I mean, you are going to solve Boolean matrix multiplication.
Yeah. You can just work modulo prime larger than n. That would work.
Like 0, 1.
Yeah. It's 0, 1.
Mod P larger
than n. Right? This is a log factor.
It's a log factor. Okay.
Okay, so, I see. So you were concerned about like bit size, actually. Yeah. Okay, good. So, this could be the end of the story, but actually people are not happy about these algorithms for various reasons, and there is actually a long line of work actually. Basically, you could call it shaving logs, but the goal is actually to design some other algorithms for this problem, for Boolean matrix multiplication, which would be kind of more natural and like easier to grasp and understand. So basically, there is a result from already 70s, which kind of shaves off from this trivial upper bound log square n, and that's partially based on like a word level parallelism, partially on some other ideas. And that was only like a few years back. It was actually improved by like extra 0.25 log actually, and then there is improvement by extra log basically and another log, and so there is this kind of indicates that people are actually interested still in other algorithms for Boolean matrix multiplication beside actually the ones which are implied by fast matrix multiplication. So The question is actually, what are limits of these algorithms? You know, these algorithms are not easy. Well, actually, this one is, say, fairly simple, but these are not actually easy at all, and they actually, some of them actually are quite complicated and rest on non-trivial results. So what's the limit of these techniques? Can we actually go substantially far beyond this n cubed by combinatorial algorithms? So what is a combinatorial algorithm? So what do I mean by that? So actually, part of this actually endeavor is to somehow come up with a reasonable definition, or would be. So like the easy definition would be, well, combinatorial is anything what's not based on fast matrix multiplication. So that would be kind of like the obvious first definition. But that's not what we really would like to actually have. So rather, actually, we would like to say what the combinatorial means, although it's actually hard to define. So we don't quite actually have a good definition for that. Except that somehow the natural way, what we would like to say is that this algorithm should kind of collect information about the product in some monotone fashion, in some sense. So there should be, in some sense, witness for the fact that the resulting matrix is something what it is. So it seems that there should be some kind of proof system, and the combinatorial algorithms, the way people actually think about them, basically are kind of trying to prove that the matrix looks the way it is. So it's trying to derive some basically information about the entries of the matrix in some incremental monotone fashion. So that's what we actually would like to have as a as a definition of combinatorial algorithms, although we don't quite manage to capture everything. So this is what we mean by combinatorial algorithm, or somehow the direction we would like to go. So why combinatorial algorithms? I already said. I mean, because they actually are interesting in its own right. Actually, people usually are much better in implementing combinatorial algorithms than like fast matrix multiplication. But moreover, it would actually give you more insight into this problem of actually multiplying matrices, and it could also give you actually insight for multiplying matrices over other semmerings. For example, like min plus semmering, which is like which computes all pairs shortest path, or it's equivalent to computing all pairs shortest path in a graph. And the best algorithm is actually algorithm by Ryan, which actually does like n cubed over 2 to the big O of square of log n. So that's so we get actually much better much better algorithm for this n cubed for this all pairs shortest path than the combinatorial algorithms get for the Boolean matrix multiplication, but still we just kind of don't get even like truly sub-cubic algorithm. So it's actually a reasonable question to understand these combinatorial algorithms, whatever are they. So the first one actually to try to actually capture what the problem is, or what could be a model for combinatorial algorithms, was actually Angluin's in '76, and she actually defined the following model, which I will try to describe, and we kind of actually extend this model in various ways. So she basically takes as a paradigm that basically, I have this matrix P and Q, and I have I'm trying to compute this resulting matrix. And what is the resulting matrix? So the resulting matrix basically, how can you get it? Well, you take a row from here, and that row actually selects some of the rows in this next matrix Q, in the second matrix. In particular, wherever you have 1, then that means actually you select these rows. And then what you do, you basically do bitwise OR of these rows, and that gives you this row. So, or you can call it union. So you basically, you think of these as characteristic vectors of a set, and you basically take a union of these 3 sets. And you do this for each of the rows. And now the question Angluin asked is actually how many of these rows do you need to actually compute, how many of these unions actually you need if you are making them kind of binary. So say I allow you only binary unions, then how many you will actually need. So in particular, you can think of our model that actually for given matrix P and Q, it actually gives you some prescription which rows to actually take union of. and you take various unions of various rows, you get some intermediate results, and eventually you actually should get all different rows which you need to assemble your resulting matrix R. So basically you get some kind of circuit of unions. So it's kind of basically like a binary circuit in the sense that it has a binary fan-in, and the operations are row unions. What is floating through these is actually rows. And what is the input? The input are rows of the original matrix Q, of the right matrix Q, and that's actually floating through this circuit. And the question is how big this circuit should be. So that corresponds basically to how many unions you have to take to actually compute this resulting matrix. And Angluin actually gives an answer, and she shows that actually, it's like n squared over log n is lower bound, and it turns out that this is actually tight. So you just need actually n squared over log n unions. And let me just emphasize, so this is not a circuit which would actually work for arbitrary matrix P and Q. This circuit actually depends on a matrix P and Q. So given I give you P and Q, and you should just design the optimal, the best way how to actually take these unions to get the result.
Yeah. This is the same result as simply for doing matrix vector multiplication in the AND/OR basis. If you have it looks like the same, using a monotone circuit, right? So if you
It
have
must not be exactly the same because like Brad proved like n cubed lower bound. Like
no, matrix vector multiplication.
Okay.
Yeah, so you have for random A, what is the complexity of a circuit with monotone circuit computing this A times X?
So matrix
Isn't
multiplication is
it
n of
n
those.
squared log n? N squared over log n.
Yeah, so the point is matrix multiplication is n of those.
Right.
And so that would imply n cubed over log n upper bound for monotone. But I'm saying there's an n cubed lower bound with no loss.
Yeah, there is an n
So there's
cubed
some
log.
there's some
Okay, so
difference.
it's
That's
not
what I'm
that,
saying.
yeah, good, very good, thanks.
Thanks.
Sorry. Here it's really, you're doing something on like maybe log n things, like all possible.
You mean these guys? So these guys are actually like n bits long because it's a row of the
matrix.
matrix.
All possible log n of them, and then like sort of picks like which one to take.
Right. So that actually gives you this extra log saving, I think. That's what you are describing is basically how to get this log n factor actually. Yeah.
It's some kind of similar to how you get like save the n factor in circuits, right? Circuits are sized.
Right. It's some way similar. So right. So that's one way how to save this. There is this n cubed over log square, and that basically like one of the savings comes from what you basically are describing. So this is actually Angluin's model, and well, if you would translate it into actually, if you would just take a trivial implementation of this, and you would try to basically, you would like to actually do real calculation using this scheme, then how much would it cost you? Well, you have these vectors of n bits, so you are taking union. So if you just apply the trivial algorithm, it's going to cost you like time n cubed over log n to actually evaluate such a witness. So if I give you the witness and you want to evaluate it, you want to verify that I am not cheating you, then you are going to basically spend like n cubed log n time on evaluating. At least that's what it seems, but actually it's not quite true. So let me actually just remind you, actually I didn't say it, but Angluin's actually lower bound is obtained just by simple counting argument. So if you just do sample counting and you count how many such circuits you have and how many different matrices are there, then you just immediately get like a random matrix is going to actually require n squared over log n guys. But if you take a random P and Q, then what happens is that actually if you look on this circuit, then once you actually take a few unions, actually you will get like all one vectors. Because like Boolean matrix, when you do Boolean matrix multiplication, actually once you take union of or log n rows, if the matrices are random, if the matrix Q is random, then you basically have like a vector of all ones. So then what happens is that actually if you look on the circuit as such, then there is going to be only about like n log n distinct unions you can actually take, because everything else is kind of like trivialized and there is nothing else to do. So if you were really actually if you would take a random matrices P and Q and try to actually evaluate this witness, then you can actually do it much faster, because if you will be clever, and you will notice that you know, you already got like all one vector, then you don't have to do anything actually. So this doesn't quite prove that it should actually be complicated to compute Boolean matrix multiplication by some combinatorial means. And so what is our model? So how we are trying to actually fix this issue with this original model? So we try to actually change the cost function you actually charge for various of these operations. So instead of actually taking cost of each operation to be like n, because it's n-bit vector, what we are going to charge rather, so we are going to think, well, maybe you actually use sparse representation for these vectors. So what we are going to charge you, we are just going to charge you basically the minimal of kind of the Hamming weight of the small of the two vectors which actually come into the action. So that basically corresponds to like having like sparse vector representation. And what else actually? So if there are two unions which actually give the same result, or actually the two and basically the values which actually enter that union, and if these two actually are the same, then we are just going to charge for it once, because you can actually easily recognize, say by fingerprinting, that you are actually taking union of the two same things. So we are not going to charge you again. And if we were to do this for the random matrices, then actually the cost is going to be just n squared log n, and here we go, we get combinatorial algorithm. So it would be very easy way to get the combinatorial algorithm, just using actually this fix. And so the question is actually what's the cost in this model? And so on random instances, the cost would be n squared log n. And but it turns out that actually, luckily for us, actually it's not, or luckily for us, or well, it depends. So if you want to prove lower bound or upper bound, so it turns out that actually even in this model, actually the Boolean matrix multiplication still costs like n cubed, at least n cubed over 2 to the square root of log n. Yeah, although this bound actually reminds you this Ryan's result, I think actually this 2 to the order square root of log n actually comes for different reasons, but it's the same function. So that's actually first result. So
you didn't tell us if Ryan's upper bound works in this model.
Say it again?
Whether Ryan's upper bound works.
So that's actually for different program, and it's not in this model. So I will get to that. Yeah. The Reynolds upper bound is for this all pairs shortest path, and it's actually not in this model. I wouldn't actually call it also combinatorial. I don't know. But this is actually a very simplistic model, and it actually is not even capable of actually implementing many of these combinatorial algorithms which I have actually shown you. So all these algorithms which actually shave these logs, actually none of them is actually, well, we can actually shave like single log actually in that model, but we cannot shave like two logs. So to actually so our goal is actually to capture all these combinatorial algorithms, but so far we succeeded basically with capturing only the first one, so shaving these two logs. And so this would be our next model. So if you look on these combinatorial algorithms, how do they actually usually operate? So what they do is they take this matrix Q or P and they break it into pieces, and then they actually operate on these pieces. And as before, they basically do these unions of small pieces, and based on actually how these pieces look like, they may do either may take either these unions or that unions, and eventually, like when by the end of the day, somehow what they do is they actually assemble all this information together, and here we go. So a natural like extension of the model I described would be the following model, which will actually allow you to break these vectors into pieces. do union of the small pieces and then assemble stuff back. So over here I would start with a row, and I would with the rows of Q. I could actually break that into continuous pieces. I could send one piece here and another piece elsewhere, and then I could actually concatenate these pieces back. So I would do that, say, at the end, and in between I would be taking union of whatever pieces I have. So that's kind of more general model, and how would I charge you actually for these operations? So it seems meaningful to actually charge, you want to charge, for proving lower bounds, you want to charge as small cost as possible for the lower bound to be meaningful. And from algorithmic perspective, you don't want to be actually more expensive than what you could charge in a real algorithm. So if you charge actually constant for breaking a row into continuous pieces, constant for concatenating pieces, that's actually algorithmically reasonable. And for taking union of pieces, we will still actually basically charge just the minimum number of ones, and we will charge again, like if there are two things which actually look the same, then we actually are going to charge only once for that. So that's the next model where we can actually prove lower bounds if the operations are actually like ordered. So first we will break the rows into pieces, then we are taking union of the pieces, and then we can concatenate the pieces.
So when you say that you're only charging once if two things look the same, is that as bit vectors?
As bit vectors.
Okay, so even if they're talking about different elements.
Right, even if they are talking about different elements, if they actually are the same binary vectors, then we actually charge just for once. Which again is actually, from algorithmic perspective, that's actually reasonable things to do, because you can easily model it by algorithm. So in this model actually, what we can show is that ideally we would like to have an algorithm which runs in like quadratic time. So it would just like order n squared algorithm, which would correspond to having matrix multiplication in quadratic time. So what we can show is that in this model, at least, it's not possible. So we get like super quadratic lower bound, in particular n to the 2 plus 1 over third, again divided by this 2 to the order square of log n lower bound, on the cost of actually doing Boolean matrix multiplication in this model. And this model is actually, as I said before, it's actually good in the sense that it at least is able to capture the first of the shaving log algorithms. That algorithm is sometimes called four Russians algorithm, although none of them was actually apparently Russian. So how do you actually, so then the next step would be how to generalize this model. And that's actually tricky, because if you try to generalize the model, well, you have to decide what the operations are going to be. You have to decide what actually the charging scheme will be. So how much you are going to pay for various operations. And if you actually charge too little, then the lower bounds that you may get will be trivial, because it will be possible very easily actually it just will be possible to actually calculate in very small, say in n squared, it will be possible to actually calculate the product of any two matrices. So you have to be somehow careful, and you have to strike the right balance to actually get some meaningful result. And so far we didn't actually quite manage to do that. And the obvious generalization would be just to allow actually arbitrary interleaving of these operations, of actually breaking into pieces and taking unions, and then maybe breaking it again and concatenate various pieces. So basically the questions which we actually leave, and which we are hoping to, someone or we will be able to actually kind of follow up upon, is what's the right mix of the operation, what's the right, basically the right model for combinatorial algorithms. So that means what should be the mix of the operations, what should be the cost function, etc. So I have a few minutes, so let me just tell you actually how we prove these results. So originally we thought that it's going to be a piece of cake to actually prove these lower bounds, but it turns out it's actually not that easy. although the model is like very restricted, as you can see, then it's by no means trivial, I would say, to prove these lower bounds, and or at least within finite trivial proof. And so what we use, we actually use these graphs which have amazing properties. So let me actually just tell you about these, because I think they should be like used more often. I know that they are used in some contexts, but this is just really amazing graphs. You wouldn't believe that they exist. So these are referred to as Růže-Semeredy graphs from '78, and these are bipartite graphs which are basically like dense. They have almost like n-squared edges, but at the same time they look very sparse. In what sense? Well, in the sense that you can actually cover all the edges by n/3, so basically linear number of disjoint induced matchings, and each of the matchings is of size like n/2 to the order square of log n. So it's almost linear sized matchings, linear number of them, and they are induced. That means that if you actually take part over here and over here, then the only edges you will see is actually the edges of the matching. So this linear number of edges. So there should be like quadratic number of actually matches. There is like quadratic number of possible edges between these three vertices and these three vertices, but you will see only linear number of them. So they kind of look locally very sparse, although they are like globally they are extremely dense. So it sounds almost impossible that they exist, but they do actually. So how do we use them? So out of these, we actually build a tripartite graph, and we build it in the following way. So we basically put here, on the left side, we put this side A, on the right side, we put this side C, and in the middle, we actually put a new set B, which is of size exactly n/3, and each of these vertices represents one of the matchings, actually. So then we actually connect. For each matching edge, each matching vertex, we actually connect to the vertices which actually take part in that matching. So if we do this, then what you actually obtain? Well, you obtain a very dense graph. So you basically, again, you get almost quadratic number of edges in the whole graph. But it has the property that there is actually going to be this many pairs of vertices, so again almost quadratic number of vertices, which are connected uniquely via a unique path. So that means, for example, these guys, the only path between them is actually via this matching, and there is no other path between them. And you will have a lot of these pairs, which again sounds counterintuitively because you have actually dense graphs. So you should expect that basically, like, typically there is between almost any pair of points, you should like expect like a linear number of paths in between, but it's actually, this is like very specific graph. So we actually use these graphs. We actually randomize the right part to kind of make it distinct, and we actually use them to prove them lower bound. So let me conclude. So we have open problems, and the kind of most interesting is actually what's the right model for combinatorial algorithms, or what would be the right proof system actually for these things. Of course, another really nice question, and I would love to actually see some progress on actually getting new combinatorial algorithms, basically breaking this n-cubed lower bound, so say getting like truly subcubic combinatorial algorithms. So I think that's a really actually interesting research question, just to speed up Boolean matrix multiplication by other means than just by fast matrix multiplication. And of course, what would be lower bounds for the model you design. So that's, thank you.
It was very clear. Thank you.